Hi everyone, this video is about propositional logic. Given a couple of statements A and B, we're particularly interested in knowing whether A and B are logically equivalent, meaning that A, if and only if B is true, and whether B can be inferred from A, meaning that the conditional statement, if A, then B, is true. Now, regarding this second bullet point, I want you to notice that, in the instance that A is true and the conditional, if A then B is true, then B must be true also. In other words, B can be inferred from A. Now, why is that? Well, if B were false, then A we know is true, and then we have the situation if A then B, where A is true and B is false. But remember, that is exactly the situation where the conditional if A then B is false. But we know that if A then B is not false. In fact, it's true. So B cannot be false. It has to be true. Okay, now another thing that you might have noticed is that I've included this word always, which technically is redundant. But I include it to point out that both A and B might be made up of smaller statements. And we want, either the logical equivalence of A and B or whether B can be inferred from A to be independent of the truth values of whatever smaller statements make up A and B. So to illustrate that, I want to give an example. So let's let A be this statement. So it's going to be if P then Q, and if Q then R. And we're going to let B be the statement if P then R. And what we want to do is examine the statement if A, then B. Okay, so here both A and B are made up of smaller statements, right? These P's, Q's, and R's. So let's see what happens to the statement if A then B. We're going to check to see whether that statement is true always, regardless of the values, the truth values of P, Q, and R. So let's start. We know that we should make a truth table. So we have P's, Q's, and R's. And then we have if P then Q. And if Q then R. And then we have the statement A, which is formed by if P then Q and if Q then R. And we have the statement B, which is if P then R. And then we have the statement if A then B. So those are the columns in our truth table. And so now we need to fill in the rows with the truth values of all of these statements. So what about the component statements, P, Q, and R? Well, they could all be true, or P and Q could be true and R could be false, or maybe only Q is false, or both Q and R are false. So in all of the values I've written down are ones where P is true, and now we look at the ones where P is false. And we finish with all of P, Q, and R being false. Okay, so now that that's over with, we're going to fill in the truth values of these other statements. So we first look at if P then Q, and both P and Q are true, which means that if P then Q is true. And in fact, remember, the only way that if P then Q can be false is for P to be true and Q to be false. And that only happens in the third and fourth rows of the table. So everywhere else, this conditional statement, if P then Q, must be true. Now, what about if Q then R? Well, it's the same thing. So the only way that can be false is when Q is true and R is false. And that only happens in row number 2. So it's false there. And in row number 1, 2, 3, 4, 5, 6. In row number 6, Q is true and R is false. So we get a false there. And every place else, the conditional is true. Okay, now we come to the statement A, which is the and of the first two statements. And remember, and is true exactly when the two component statements are true. So A is true here. It's going to be false there, false, false. And now here again, the two components are true, so the and statement is true. So this is false. And again, we have true and true. Now B, again, is this conditional if P then R. So remember, that can be false. That's false exactly when P is true and R is false. So that happens in rows 2 and 4. So every place else, B is true. And now finally, we come to the statement in question, which is if A, then B. So remember, if A, then B is going to be false exactly when A is true and B is false. So we look for all the places where A is true, so that happens here, 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 and here, and we look over and check to see whether B is false, and it never is. Right? So what that means is that this implication is true. And it is true regardless of the truth values of the original statements P, Q, and R. Now what you might notice is that okay, we had to do a lot of work to check that this statement, if A, then B, is true, right? We had to do this massive truth table with the three sort of individual component statements, P, Q, and R. And it might strike you that this is an unwieldy way to deal with things, especially if A and B were comprised of even more elementary statements. Like maybe there would be 4 or 5 or 6 or 8 statements, and that would make the corresponding truth table have more and more and more rows. In fact, it's it's exponentially more rows depending on the number of elementary sort of component statements you have at the beginning. So what we want to do is find or sort of think about some other way that we might determine whether an implication, if A, then B, is always true, that does not involve using truth tables. So on the previous slide, we were discussing certain statements in particular wondering, how to determine whether they are always true. So there's a special name for a statement that's always true regardless of the truth values of its component statements. So that such a thing is called a tautology. So here in the bullet points we have a couple of examples. So in the first bullet point we have P or not P, which apparently is a tautology. So let's check that. So we have P and not P, and P or not P. So the truth table is very short here. So P can either be true or false. When P is true, not P is false. When P is false, not P is true. Now remember, an or statement will be true precisely when at least one of the component statements is true, and that happens in both rows. So P or not P is always true, and so this is a tautology. Actually, the statement, P or not P is a tautology. Okay, now what about the second bullet point? Well, this is a more involved statement, and actually it's a rather famous and useful statement, as we shall see in a little bit. Let's analyze that statement. So here our basic components are P and Q. If P, then Q also plays a role in this. And then we've got P and if P, then Q. And then finally we have the statement we're interested in, which is P and if P, then Q. Implies Q. All right, so there's our columns for our truth table. So first we list the values, truth values of P and Q. So they could both be true, or P could be true and Q could be false, or Q could be false, or P could be false and Q could be true, or they could both be false. Okay, now for the third column, if P, then Q, remember that's going to be false exactly when P is true and Q is false. And in any other scenario, it's going to be true. Okay, now we have P and if P, then Q. So we're looking at the first column and the third column, and that's going to be true exactly when both are true. So that happens here, and it happens nowhere else. All right, now we're in the final column, which is the statement that we're interested in. And remember, this is an implication. And the only way it can be false is when this thing is true and Q is false. So that's the only way that this statement can be false. So the first statement being true, that happens in the first row. And then I look over at Q, and I see it's also true. Now, in every other instance, this first statement here is false. So in every single row, we get T's. Okay, now most statements are not tautologies. And so, maybe it would be a good idea for you now to think about some kind of statement that is not a tautology. In fact, maybe you could pick one right from this slide. Here we introduce some notation for tautologies. So first, if we have an if-then tautology of the form if A then C, that is going to be denoted with a double arrow, right? And remember, that means that the conditional statement if A then C is always true. So I just want to remind you that if you want to verify that if A then C is always true, it suffices to show that if A is true, then C must also be true. Now, sometimes these if-then tautologies involve and statements at the beginning, like A and B. And historically or commonly, those statements are listed vertically like this. Now, I know that seems like a waste of space on a page, but that is the convention for how these are denoted. Okay, so you might recall from the previous slide that we verified that this statement is a tautology, and in our new notation, we would indicate that like this. So we can infer Q from P and if P then Q. Okay, so that tautology that we just mentioned a moment ago has a name. It's called modus ponens. So it tells us that if P and if P then Q are true, then Q is forced to be true. And if you think about that, aside from the symbols and all of that other stuff, it makes perfect sense, right? If you know P and you know if P then Q, then you should know Q as well. So that's the upshot of modus ponens. So an example of modus ponens would be as follows. If Andrea is late, then Briley is late. Andrea is late, therefore Briley is late, right? It makes perfect sense, right? Okay, now there's another important related tautology called modus tollens. What it says is that if you know if P then Q, and you know not Q, then you know not P. So here's an example of modus tollens. So it says, if Andrea is late, then Briley is late. Briley is not late, and therefore Andrea is not late. Okay, here we're going to verify the modus tollens tautology using a truth table. So how do we do that? Well, we've got component statements P and Q. The conditional statement if P then Q is involved in modus tollens. And we also have not Q and if P then Q. And then finally, we have not Q and if P then Q implies not P. Okay, so this last statement right here, the long one, not Q and if P then Q implies not P. That is the substance of modus tollens. So what we're expecting in this last column is to have all T's all the way down. Okay, so again, we start as usual. We're going to list off our possible values, possible truth values of P and Q. Cover all possible settings. And then we have the conditional if P then Q, which remember, the only way that's false is if Q is false and P is true. Everywhere else it's true. And now we look at not Q and if P then Q. So remember, the and statement is going to be true exactly when both of the components, not Q and if P then Q, are true. So that only happens in the last row. Everywhere else, it does not happen. Okay, and then finally we have the implication or the conditional statement. So if, not Q and if P then Q, then not P. So remember, a statement like this, the only way it can be false is when the first bit is true and the second bit is false. So the first bit is false, actually, in the first three rows. And so the conditional statement is automatically true. Now, what about in the last row? Well, the first bit is true, but so is not P. And so we get T is all the way down. So modest tollens is indeed a tautology. So here we have a bit more notation involving tautologies. In particular, if we have a logical equivalence tautology, A if and only if B, that will be denoted with a corresponding double wide arrow. So here we have some examples, De Morgan's laws. So the first one says that the negation of P or Q is logically equivalent to not P and not Q. And the second one says that the negation of P and Q is logically equivalent to not P or not Q. So let's verify the first one using a truth table, and maybe you all can do the second one as an exercise. So let's write down a table. Maybe we do PQ, P or Q, and then not P or Q. And then maybe all at once we'll do not P and not Q. And then finally we have the if and only if statement. So that would be not P or Q. If and only if not P and not Q. Okay, so those are the columns for our truth table. So you know the drill now. We're just going to write down the possible truth values for P and Q. So P or Q, remember that statement is a statement that really wants to be true. In fact, it's false exactly when both P and Q are false. So it's false here, and it's true everywhere else. It's true when at least one of P or Q is true. Okay, now in the next column, we're just negating the previous column. All right, now over here in the next column, we have not P and not Q. That is a statement that is true exactly when not P is true and not Q is true. And that will happen in this very last, this fourth row, right? P and Q are both false in the fourth row. That means not P and not Q are both true. So this and statement will be true. Every place else, it's going to be false. And now we have the statement in question that we're trying to check is a tautology. And what are we doing? Well, we're going to look at the previous two columns and check to see when their truth values are the same. Well, they're the same there, they're the same there, they're the same there. In fact, they're both false in the first three rows, and then the last row, they're both true. And so lo and behold, this first of De Morgan's laws is a tautology. So before we go any further, maybe it's worthwhile for us to recap a couple of things. So first of all, we have the tautology, if A, then B. That allows us, when that is in place, that allows us to infer statement B from statement A. That means that if A is true and this tautology is in place, then B is forced to be true. Now, on the other hand, this tautology A, if and only if B, says that A and B are logically equivalent, okay? So that means that we can, any place we see A, we can substitute B for A, or vice versa, without losing anything, right? A and B are, from a logical standpoint, equivalent statements. So we can also infer B from A, and we can infer A from B. Now you might be wondering where those two are coming from. Well, these latter two bullet points come from this tautology, meaning that, you know, P and Q are logically equivalent when Q can be inferred from P and P inferred from Q. So it might not be a bad idea to check this tautology here with a truth table. So early on in this video, we talked about our desire to rid ourselves, at least partially, of truth tables because they can become unwieldy. And now I'd like to return to that idea. So we begin with looking at tautologies of the form if A, then C, which are called inference rules, by the way. And we want to be able to verify such things without resorting to truth tables. And our method is going to be as follows. So what we want to do essentially is supply some intermediate statements between A and C where we can establish sort of bit by bit some inference rules. So we start with A, and from there we infer B1 and A. And from there, we take another step and infer B2, which now joins B1 and A. And then we infer B3 and so on, which again joins the previous statements. And ultimately, after we supply enough intermediate statements, then maybe we will be able to eventually infer C. So that's sort of the idea, is to supply some intermediate statements. Now, this method of supplying intermediate statements has a name. It's called a proof sequence. Now, why does it work? Why should the tautology A, if A, then A and B1, and if A and B1, then A and B1 and B2, why should that culminate in this tautology, if A, then C? Well, we already sort of saw the answer to that on a previous slide. So this method works because if you combine these conditional statements with an and, then that implies always if the first, then the last. Right, so that should look familiar to everyone. In fact, we did verify this on a previous slide using a truth table. So if you want to check that, you could pause the video and go back a few slides and you'll see where we did this. We didn't use A's, B's, and C's. We used P, Q's, and R's, but it's the same idea. Now, the next question, though, is, okay, well, where do we come up with these intermediate statements? So yeah, that's a problem that we need to construct proof sequences. We're going to use some basic tautologies called derivation rules. So you can think about these as sort of tools in our tool belt that we're going to use to construct proof sequences. So there are two varieties of these. There are equivalence rules, which where we are declaring two statements to be logically equivalent. And then there are inference rules where we're declaring that we can infer one statement from another. So here are some basic equivalence rules that we will be using. Some of them we have verified and others we have not. But if you're wondering or doubting one or more of them, you can always check them using a truth table. So the first one is that P should be equivalent to the negation of P. Hopefully we wouldn't argue with that. This second one is one that's maybe not as obvious, right? It's saying that if P then Q is equivalent to the statement not P or Q. Now this has a name. It's called implication. So this equivalence rule is called implication. And, it might be a good idea to check that with a truth table. Now in the next two, you see something that should look familiar, right? These are De Morgan's laws. In fact, this first one, I guess I should tell you it has a name. It's called double negation. Just takes you back to where you started. Okay, now the next bullet points are just claiming that the order of statements in and or doesn't matter. Doesn't matter whether P or Q is the same as Q or P. So these are commutativity. And then finally, we have some equivalence rules that have to do with groupings. And as you might guess, these are called, this is associativity. Okay, so these are tools that we are going to use in the future to construct proof sequences. On the previous slide, we introduced the idea of derivation rules, which are going to be useful to us when constructing proof sequences. And of course, we recall that these derivation rules come in two types. So we have equivalence rules, which are logically equivalent tautologies. And then we have these things called inference rules, which are, if-then tautologies. Okay, so on the last slide, we talked about some of the basic equivalence rules that we would use. Here on this slide, we identify some of the basic inference rules that we would use. So the first one should look familiar, right? So that's modus ponens. And the second one should look familiar too. It's modus tollens. And then here, this is just sort of a matter of notation regarding and. So if we have P and we have Q, then we have P and Q. So this is called conjunction. And, if we have P and Q, then of course we have P. This is called simplification. And the final one, if we have P, then we have P or Q. That's called addition. So all of these inference rules, as well as the equivalence rules on the previous slide, can be checked using truth tables in the way that we, checked some of the other tautologies. Okay, now, at long last, we're going to verify an inference tautology. Remember, such a thing is called an inference rule without resorting to truth tables. So our method is going to be to produce a proof sequence. And we saw on an earlier slide that the idea of the proof sequence is to supply some intermediate statements between the statement we're starting with, which is this A, and the statement that we wish to finish with, which is this C. So remember, to show an inference tautology like this, it suffices to show that if A is true, then C must be true also. Now, with that in mind, what specifically will this proof sequence look like? So it's going to take the form of two columns. So we're going to have, in one column, we'll have some statements. And in another column, we're going to have reasons. So we will number our rows. So in row number 1, we're going to start off with the things that we are assuming to be true at the moment. So we're given that P is true, right? Remember, to prove the tautology, if A, then C, it suffices to show that if A is true, then C must also be true. So for A to be true, what does that mean? Well, we're given this sort of a list of statements, P, if P, then Q, and if Q, then R. So all of those we're going to be given as true. All right, so far, so good. Okay, now I need to go beyond to supply our first intermediate statement. So what you might notice is that I know P and I know if P then Q. So if you look at your list of derivation rules, under the list of inference rules, there's this thing called modus ponens, which says that if we know P and we know if P then Q, then we must also know Q. So that's modus ponens. And we're going to list the line numbers where we're using modus ponens, namely line number 1 and 2. All right, now remember, our goal is to infer R, right? So we're almost there because, look, I know if Q then R, and I know Q, so I could go ahead then and infer R from that. Again, this is modus ponens. This time with lines 3 and 4. And now we see that we are finished, right? We have taken our given statements here and supplied some intermediate statements, and then finally ended up with the statement that we wished to achieve. So that is a proof statement, or a proof sequence for this tautology. Okay, here we have another example of verifying an inference tautology using a proof sequence. So again, this involves supplying some intermediate statements that take us on our way to the statement that we would like to infer from the original statement. So we have some statements. And some reasons. And as before, it's probably a good idea for you to have your list of derivation rules in front of you. So our first statements are always going to be the given statements. So it's going to be if P then not Q, and if R then P and Q. All right, so those are given. Right, so again, at the risk of repeating, right, the idea is if you want to show an inference tautology is true, you assume that the original statement A is true, and you show that the final statement C is then forced to be true. Now, this original statement A, for it to be true, since it's an and statement, that means that all of these given things, all of these component things must also be true. And so that's why we're listing them as given. Okay, now, well, we've listed the given things, and we need to sort of make some progress toward obtaining not R. So, one could sit and stare at this for a long time maybe and not make much progress. What I would recommend doing is this, that we can rewrite statement 1 as not P or not Q using the implication rule. So this is an equivalence relation, this implication. It says that, remember that if P then Q is the same as not P or Q. Okay? So these two are logically equivalent. So that's what implication says. So I'm just taking that, and I'm using implication in line 1. Now, my second given statement involves an and I can take this or statement in item 3 and turn it into an and statement if I use De Morgan's laws. So there we're using De Morgan in line 3. Now, if you look at lines 2 and 4, I know if R, then P and Q. I also know not P and Q. And then if we apply modus tollens, that should give us not R. So this involves lines 2 and 4. And that's the end, right? We have now supplied intermediate statements, namely statements 3 and 4 were intermediate. And then we wound up inferring the statement that we wanted to infer, namely this not R. Okay, now you might notice from this that even though we're saving space maybe over truth tables here, it can be hard to sometimes to think about what statements and reasons to provide in the course of these proof sequences. Okay, here we have a final example of a proof sequence for an inference tautology or an inference rule. This one will be a little bit more involved than the last two that we've done. Before we get started, I want to point out that two different people might write two different proof sequences for the same tautology, and they can both be right. Okay, so maybe you will want to just try your hand, pause the video, and try your hand at this particular tautology. You may come up with a proof sequence that looks different from the one that I'm about to write down. Okay, so again, remember this involves making a table of statements and reasons. And so we'll go all the way down here. So we first put our given statement. So it's P and Q or R. And we've got not P and Q. So those are given to us as our starting point. And now we need to go do something. So the very first thing that I did here was to apply De Morgan's law. So not P or not Q. So that's De Morgan. In 2. And then I can take, using the implication equivalence rule, I can write this as if P then not Q. So that's the implication. In line 3, and then, well, I would like to use modus ponens on item 4, but the problem is that I don't necessarily know P yet. But if I look at item 1, I can use simplification. Right, see, I have in item 1, I have P and something. So that means that I can infer P. So that's the simplification equivalence rule in item 1. And now I can use modus ponens to compute not, or to infer not Q. So this was items 4 and 5, where we're using modus ponens. And then in line 7, we can again go up here to line 1. We already used simplification to infer P. We could also use simplification to infer Q or R. And remember, Q can be written as not Q, or R. Remember, this not here only modifies the stuff that's immediately next to it. So that's double negation. And we did that in line 7. And then we can use our implication equivalence rule again to say that this is the same as not Q. If not Q, then R. So that's implication in 8. All right, now notice we have not Q and we have if not Q, then R. So that allows us to compute or to infer R from modus ponens. And that's in lines 6 and 9. And now we're nearly done, right? We're trying to obtain P and R. We're trying to infer that. So I know P from item 5, and I know R from item 10. And so that means that I'm able to infer P and R by conjunction. So that's in 5 and 10. And that's our proof sequence.